Section 14.2, Probability. So, something to note is that the probability of event E happening is equal to the number of the event E over the number of the sample space. So this basically relates to the number of outcomes favorable to event E divided by the total number of possible outcomes. So in shorthand, part over whole. So part 1 is just some review of basic probability. Given the spinner to the right, the sample space or possible outcomes would be S equals ABCD because those are the choices on your spinner. An event would be like spinning D. So the probability of the spinner landing on D, notated P of D, would be 1 out of 4, meaning there's one section labeled D right here, out of the total number of 4, which are all equal sizes. And it's important to note that since they are all equal sizes, they are all equally likely to occur. Okay, so given a standard deck of cards, the sample space would be 13 hearts, 13 clubs, 13 spades, and 13 diamonds. So below are some possible events, so let's find the probability of each. So, the probability of choosing the 3 of hearts. Well, that is one card, your part, out of all of 52 cards you have to choose from. So then the probability of choosing a spade, any spade, is going to be 13 over 52, which simplifies into 1/4. And then the probability of getting a jack, there's 4 jacks, one of each suit, out of 52 total cards, which is 1 out of 13 when we simplify it. So then, if we go back to the spinner, let's find the probability of spinning an F. Well, the probability of this is 0 because it's not possible. F is not a choice out of A, B, C, and D, so 0. Then, the probability of event 2, which is a letter between A and D, inclusive. So this means including A and D and the letters in between. Well, B and C are in between, and then including A and D means all of them. So the answer here is 1. So you can also say this like you have, well, the probability of spinning A is 1 out of 4, plus the probability of spinning B is 1 out of 4, plus C, plus D, which gives us 1, or you know it's 100% possible, which gives us a probability of 1. Section 2 is complementary events. So this is the definition for it. So basically, the probability of E, an event E not occurring, is to figure that out, we're going to do the probability of it occurring and subtract it from 1. So let's take a look at this. Given a bag that contains 8 blue marbles, 5 red marbles, and 2 orange marbles, what is the probability that a randomly selected marble is not red? So the easiest way to do it is doing it as a complementary events. We have the fact that there's 15 marbles total in that bag. So the probability of not choosing a red is going to be 1 minus the probability of choosing a red. And this equals 1 minus, we have 5 red marbles out of 15, which gives me 10 out of 15, which simplifies to 2/3. Or, without doing complementary events, you could take the probability of everything that's not red. So, the probability of it not being red means then it's the probability of it being other things. Well, we have blue, or probability of it being orange. Now, this or right here is denoted by an addition sign. The plus sign means or. So this is the probability of blue is 8 out of 15. plus the probability of orange is 2 out of 15, which is 10 out of 15, which simplifies to 2/3. Okay, so example 2, a single card is drawn from a well-shuffled deck. What's the probability that the card is not a spade? So that means the easiest way to go about this, I like method 1, complementary events, is going to be the probability not a spade is equal to 100% or 1, all the total possibilities, subtract getting a spade, which stands for everything else. And this equals 1 minus, there's 13 spades out of 52 cards, which simplifies to 39 over 52, which simplifies to 3 over 4. Okay, so we have a word problem here. A ferry is powered by 2 engines, one forward and one aft, meaning one in the back. The factor error testing shows that the probability that the back engine failing is 0.05. The probability of the forward one failing is 0.03, and the probability that they both fail is 0.012. So what's the probability that the ferry completes its next trip? So it's important to note that they added in, the trip can be completed as long as at least one engine is functioning. So this means the probability of completion of this ferry trip is going to be equal to 1 minus the probability that both engines fail. Because if they both fail, that is the only way that we won't make it. So 1 minus not making it is going to equal us making it, so completion. So 1 minus the probability, or probability of both failing, which is 0.012 as stated. So the answer is a 0.988 probability that they will both, or that we will complete it, that they both won't fail. So complementary events, completing the trip is complementary to both engines failing. Okay, so let's consider that we roll 2 die at the same time, and we're going to use that chart to the right. So we're going to find the probability of all of these events that are occurring. So just to note, the probability, there are a total of 36 rolls here. You see 72, but keep in mind you're rolling 2 die at a time, so 36 rolls. So if you roll 2 threes, that can only happen one time. So we have a 1 out of 36 probability. So if you roll and you get a 5 and a 6, that's going to be right here and right here, a 5 and a 6. So that is 2 out of 36, which simplifies to 1 out of 18. A probability of a 5 and or a 6. So if we're doing a 5, just in general, that's right here. And then a probability of 6, well, that's right here. I don't want to overlap because then I'm going to count a die twice. So you have 6s there and at the bottom, and I almost forgot you have 5s here too. So we're not just taking into account like a 1 and a 5, but also that we could roll a 5 first and a 1 first. So if you add up all of those pairs, we get 20 out of 36, which simplifies to 5/9. Okay, now if we want at least 1/6, so at least 1/6 is going to give us down here, these are all the 1/6s. And I can also circle 2 because it's at least 1. And then we also want these right here. I'm not going to overlap so I don't count the same roll twice. So this gives me 11 out of 36. And then if you want exactly 1/6, that means I'm just going to erase this option down here because it's 2 6s. So then I have 10 out of 36, which simplifies to 5/18. So then if we have no 6s, so we're going to take everything except a 6 right here, which gives us a lot to count. Or let's do it this way. Let's do it. If we have no 6s, that means I'm going to do a complementary event. 1 minus the probability of at least 1/6. Well, I just found that out, 2 above. So I have 1 minus 11/36, which equals 25/36. And if I were to count that all the rolls in that orange box, I'm also going to get 25. So then moving on, a sum of 7. Well, we can actually look at sums diagonally. So 7 is going to be 6 and 1, 2 and 5, 4 and 3, 3 and 4, 5 and 2, and 1 and 6. So this diagonal right here. So what's that give me? 6. So I have 6 out of 36, which simplifies to 1/6. So now if we have a sum greater than 8, we are looking at down here at the bottom where we have 8. Well, that doesn't count because it has to be greater than 8. So we have 6 and 3, 4 and 6, 5 and 6, 6 and 6 right here. And then 4 and 5 right here. So this gives us 10 rolls out of 36, which simplifies to 5/18. And the last one is a sum of no more than 8, meaning, well, if it can't be more than 8, so a sum no more than 8, let's do a complementary event. 1 minus the probability of a sum greater than 8. And we just did this, so we're going to have 1 minus 5/18 equal to 13/18. Okay, so part 3 is probability and counting. So we're gonna work with combinations like we did, or like we've worked with before. So I have 13 cards are dealt from a well-shuffled deck. What is the probability that the 13 cards contain all red cards? So we have a bunch of options here. So we're going to start by saying this represents the number of all combinations of 13 red cards. So this is our part. This is the specific we're looking for. So what is this all out of is the number of all combinations of just choosing 13 cards. So we're going to use a combination here because I have 52 total cards. I'm just going to choose 13, but then there's even like more to it. It's not just choosing 13, it's choosing 13 that are also red. So we're going to take that part over the probability of just all the choices that if we were to choose 13 in general. So this is written as, I'm going to start with the denominator. So we have 52 cards, and we want to choose 13 from that. So that's the total. Any 13 cards from 52. So then, what's the probability then that they're all red? Well, we have 26 red cards to choose from. And again, I want to choose 13 cards. So that's the part over the whole, and when we simplify this, it's extremely small, and we get 1.64 times 10 to the negative fifth. Okay, so now if we want all face cards. So this is actually not possible, so the probability is 0. And why is it impossible? Because there are only 12 face cards. So I can't have 13 face cards at all. Okay, and this last one is pretty tough. So it says, at least 13 red cards. So at least implies a couple different options. So out of those 13, if we want at least 11 red cards, that means we want the probability of 11 red cards, because 11 is at least. Or we could have the probability of 12 red cards, because that's still at least 11. Or we could even just have all 13 be red. So what's that probability? Now, since I'm saying or, this implies that we are going to add all three of these probabilities together. Okay, so how does this look? Each one, let's do each one at a time. Or one at a time. So, here's my first proportion. So, if it's all red cards, that means we are still choosing, out of 52 cards, we're choosing 13. So then if I want 11 red cards, that's going to be 26 red, and I'm going to choose 11. Well, that's only 11 cards. So this represents all the red cards, but we're not done. I want 13, and I only chose 11, so I have 2 more that I could choose from. So I'm also going to have 26 black cards and choose 2. And this has to be black because I only have 11 red. So if they're not red, they're black. So I have 11 red cards, therefore the other 2 must be black. Now, I have no choice. This is definitely an and statement. So that means the probability of at least 11 red means 11 red and 2 black. So and is multiplication. And I'll do the dot. Multiplication. Okay, so let's do the probability of 12 red cards. Again, we have 52 cards and we want 13. So if we have 12 red, we have 26 choosing 12, and that means that we need to consider the black cards. So we have 26 black cards, and we only want to choose 1 now. And in between those, we're going to have a plus sign. And then our last one. Our last one is just the probability of all 13 being red. So that means we have 52 and we want 13, but out of those 13, we are going to choose out of the 26 red cards, all 13. So this only has one part. There's no other and to this. Now, what I recommend you do is plug each fraction into your calculator, get 3 decimals, and then add them all together. So if you do that, you get about 0.0043 0.37. This is your probability. Now, something to look for that you have to make sure of. Down here at the bottom, you always want 13 because the very beginning of this problem said you're going to choose 13 out of the 52. Well, in each category I have in the numerator, I have red and I have black cards. Now, those two numbers, 11 and 2, have to add to give you 13 to make sure you've accounted for all 13. And the other one, you have 12 plus 1, which gives you 13. And then over here on the right, since we only have one option, it is 13. So always make sure that those right side numbers, the number you're choosing for per category, add to give you the number you're choosing on your denominator. Okay, your last example. A lot of 20 TV sets consists of 6 defective sets and 14 good ones. If a sample of 3 is chosen, what is the probability that the sample contains all defective sets? So, we have a total of 20 sets to choose from because we have 6 defective and 14 good ones. So, we have 20 and we want to just choose 3. Okay, stop, Sawyer. So, it said if a sample of 3 are chosen, so therefore I have 20 choosing 3. 20 total possibilities, 3. But what do I ask? Well, what's the probability that they're all defective? Well, what's the total defective I have? 6. So out of those 6, I want them all 3 to be defective. And when I do this, I get 0.01754. And the last question. What is the probability of choosing 2 defective and 1 non-defective? So again, we're choosing 3 out of 20, but then 2 are defective, so 6 defective, so I'm going to choose 2. But 2 doesn't add to give me 3, so I need to choose one more. So it's and times the 14 good choices, and therefore I'm choosing 1 left over from that. So this probability gives me 0.18421.